recording. Okay, so we should see the little red light on the top of our Zoom screens, which tells us we're recording. And back into the presentation. Okay, let me just make this full screen. There we go. Okay, so I wanted to start with just a kind of another one of these sort of funny examples of a design fail where the designer is not thinking about the end user and how the end user is actually going to use the product. And this is actually from my childhood. So you guys are probably too young to remember, but in the 80s, the US engaged in this big federally funded war on drugs, and the impetus for the war on drugs came out of the first lady's office. So Nancy Reagan, who was the wife of Ronald Reagan, who was president at the time, and part of what they were trying to do was educate K through 12 students about the dangers of doing drugs. And so to try to get that message across to students in schools, they generated these pencils that had the message "too cool to do drugs" on them. And so when I was a kid, these came to our school, and what the designers failed to take into consideration is the way that the pencils would actually be used by the end users, who are the students, which is that they're the old style kind of wood and lead pencils, wood and graphite pencils, and when you sharpened them, when the pencil broke and you sharpened the pencil, it would shorten the pencil because you'd have to, chew down some of the wood to expose the fresh lead. And in shortening the pencil, the message changed from what they intended it to say, which was "too cool to do drugs," to which was, sort of a don't do drugs, kind of drugs are bad message that they were trying to convey, to cool to do drugs, and then just do drugs, and then drugs. And so the thing at school, of course, all of the kids who were trying to be funny would get a hold of these pencils and would intentionally sharpen them down to the point where they said something other than "too cool to do drugs." And so I remember when I was a kid, the greatest thing to have when you were a little kid running around school was a pencil that had the word just "drugs" on it. There were a bunch of students that would intentionally write with an extremely short pencil that said "drugs." Just they had a pencil from the government that said that on it. So anyway, kind of a funny story again from my childhood that just describes what happens when a designer doesn't think about the end user and how they're going to use the product. So anyway, today we're going to talk about dynamics as a refresher. So we've talked about fluids, we've talked about thermo. Today is dynamics, and then there's still going to be DML and Mech 1 out in front of us for later this week and the following week. But I did want to just mention that I sent out the cell phone survey, and it's the same two questions: what went well, what could improve, and then the third question, as I've done with thermo and fluids, asks you to kind of rate your competence with the subject of dynamics. And interestingly, with fluids and thermo, I didn't ask for this, but most students rated their competence on a Likert scale, a 1 to 10 scale, where 1 is bad and 10 is good. So the vast majority of you guys just did that spontaneously, which was interesting. Um, and not so good. So fluids, kind of the average was sort of like 3-ish, and thermo, it was 6 or 7. And a lot of, I think, that is because it's just been a while since you've taken those classes, and so some of this stuff probably is a little bit rusty. But if you could give me sort of the same sense of how you're doing or how you feel about dynamics, that would be helpful. So if you could answer the cell phone survey with a dynamics competence level, that would help me to see how much material I should be posting. Speaking of posting material, I did have an incident over the weekend. My wife and kids were driving and ended up getting into a car accident. Not very serious. They were stopped at a red light, and somebody else who was stopped behind them started to move before the light changed and bumped into them, and so it didn't hit them at very high speed. Thankfully, nobody was hurt. Our car was undamaged. Their car had a little bit of a dent in it in the bumper, but we did have to call the police and get the insurance companies to come and take a look and stuff. So it did suck up a little bit of my time that I had earmarked to kind of flesh out the Canvas site, and so I'm now behind, and so I've got the entire fluids refresher page posted, the thermo refresher page I have posted, but other than the OER textbook for that material, I don't have any of the content up, so I got to populate that today. The week two material, the synchronous, asynchronous, and suggested reading content still has yet to be posted, so I got to do that as well today. And then the dynamics refresher material, I also have to put that up. So I'm a little behind, but I did have a little incident this weekend, so I appreciate your patience with me as I get caught up today, and get all that stuff posted for you on Canvas. But the feedback from the survey tells me, like how much dynamic stuff I really need to post. Um, so there's that little bit of housekeeping, and then the other bit of housekeeping is with the reverse engineering reports. So we do now have all the artifacts in MAEC 010, the design lab, and you can, if you elected to pick your kit up, you can pick it up, and if not, if you elected to have your kit mailed, Noel, I think, will put them in the mail by the end of the day today, so they should be in hand, I would think, like Friday if you're local, maybe Monday at the latest, I would hope. And once those kits are actually shipped, if you elected to get yours mailed, you'll get a tracking number, so you can kind of keep track of. It'll come in your email, so you can keep track of where the kits are. If you did elect to pick up your kit, Noel is available today until 4 o'clock. In the design lab at MAEC 010, to kind of give you your kit. He's got them all boxed up, sitting on a table. The trick, though, here is that we have to maintain um, COVID-19 pandemic protocol. So we cannot have more than a certain number of people in that space at any one time. Everybody has to be masked, cleared to come to campus, and maintaining social distancing. And so what we've ended up doing is there's 4 ways to get into the design lab, and we've locked the doors, blocked the doors, so that only one entrance is accessible from the outside for you guys. So you could conceivably come in through DML, but that door should be closed. You could also potentially come in from the south side from where Mike Griffiths' office is, but that end central receiving, but that door is also closed, and you should not be able to get in that way. Um, you can come in normally from Gail Lemon from the outside street. Oftentimes you'll see the Gator Motorsports team kind of sitting out in the same spot. There's actually a door that gets into the design lab from right where the Gator Motorsports guys are working usually. That door is also closed and locked. So there's only one way in, which is if you come in through the entrance that is facing Ryan's Hall. And so there's a little sort of alleyway, kind of a 1-lane road here between MAEC and Ryan's Hall. And if you go to the second door that you encounter as you walk south, that door should be unlocked. And when you open that door, it'll open right into MAEC 010, which is the design lab. And Noel has set up right there at that door a table that has the reverse engineering report kits in boxes. You get the fire piston assembly, a set of calipers, and some safety glasses. And we've talked about why in the past you need safety glasses as you're working on the RER artifact. So it's all just laid out there in boxes on a table. So if you just pick up a box will have all 3 of those items in it, and then there's a little ledger where you can sign your name legibly, please, to indicate that you have your artifact. So as soon as you have your artifact in hand and they've signed the ledger, just turn around and head right back out, because we can't have more than, I think it's 14 or 15 people in that space at any one time. So there's really only enough capacity for one of you to be in there at any time. So if more than one person shows up simultaneously, I appreciate if you guys just queue up outside. Again, put your masks on, maintain social distancing at least 6 feet apart, and just as orderly as you can, just go in one at a time, grab your kit, sign off on the ledger, and leave, and then the next student can come in and so forth. And Noel will be there until 4 o'clock today. If we're not able to get everybody their kits by today, he could be there again on Thursday and on Friday. But hopefully, we'll have them all distributed by Friday, at least for the folks who are interested in the on-campus pickup. So let me pause there and ask if anyone has any questions about any of the logistics of the kit mailing or the pickup before I move on to the course content. Good. Okay. So Noel will be here again until 4 o'clock today. So you can get it today, or if not today, he'll be there starting at 10 a.m. tomorrow. So you can pick your kit up then. All right. So we were meant to talk about mass spring dampers, which is a topic in dynamics. And I'm going to, as I've done before with the thermo and the fluids, to tie this in to the reverse engineering report, so that it gives you sort of a leg up, a beginning on the type of dynamics analysis that you might consider doing as part of that report. And so what I'm going to do is run through kind of the explanation or the derivation from first principles for how you come up with the spring mass damper equation for this simple system. And then I'm going to modify this so that it corresponds to the dynamic equation, the equation of motion for the piston on the fire piston assembly after you've done the auto ignition process, right? So after you've smacked the piston down and got the char cloth to spark, to ignite, then you're gonna take your hand off the piston, right? And something is going to happen. And what is that something? Well, that's what this equation tells us. And so that's what I'm trying to sort out. But the way that I'm going to do it is to give you guys just a refresher on how the original spring mass damper equation comes to be, and then we'll use that sort of as a baseline for a modified dynamic equation for the piston as it's recovering from the compression process. So we've got just a mass here that's attached. The mass is able to move in the x hat direction, and it's attached to a solid wall with two different attachments. So there's one mechanism which is a linear spring, and then there's a second attachment which is a viscous dashpot. And at least in this drawing, this mass has got a forcing function which is just f of t. So somebody is pulling on the mass with some force that may or may not change as a function of time, and the mass is able to move again in the x or x hat direction. And this here, this equation that I boxed in orange, that is the equation that describes the motion of this mass as it's pictured here in the schematic. So this first term is the spring force associated with the linear spring. The second term is the dashpot force associated with the damping of the dashpot, and then the third term is the acceleration of the mass itself. So we're going to work out how to go from basically a free body diagram to all of these terms and reconstruct this equation for a system of interest. So the way that I'm going to do that is go through four separate steps. So I'm gonna create an origin. I'm gonna define my position, velocity, and acceleration variables. I'm gonna draw a free body diagram, and then I'm gonna apply Newton's second law as a force balance to the free body diagram to back out this this equation. And so first step is to set a coordinate system. Now this seems really sort of silly, right? Because by now you guys have drawn enough free body diagrams that it's like, oh, I don't really need to set a coordinate system. But I would encourage you, every time you do a dynamics analysis, anytime you draw a free body diagram, please set the coordinate system, even if it seems sort of silly and redundant to do so, just so that you have it and have something to refer to and have an origin that you can count from. It just, if you make a mistake, it's much easier to catch that mistake if you've determined what the origin is. So I'm going to set the origin as this upper right hand corner of the mass, in a situation where the mass has basically been left alone and allowed to settle to a state where the force produced by the spring is zero, right? So the spring is not elongated, not compressed. It's at its rest length, and as a result, the force on this mass from the spring is zero. And so I'm going to set the origin at that top corner. So x hat goes off in the right direction, y hat goes up, and z hat is coming out of the screen towards us. So we've got Euclidean x, y, z orthogonal coordinates there. So got that figured out. Step number two is to define my variables. And really, this is just semantics. I could have left things as position, velocity, and acceleration if I wanted to, but it's easier to solve a differential equation where everything is the same variable. And so all I'm doing is just renaming my position vector as x multiplied by the direction x hat. My velocity vector is just the first derivative of position with respect to time in the x hat direction. And my acceleration vector is the second velocity of position with respect to time, also multiplied by the x hat vector. So that gets us those definitions. And now I'm going to draw my free body diagram, which seems a little weird, right? Because it might appear like I've got the arrows in some cases kind of going in the wrong direction. The beauty of a free body diagram is that it doesn't matter, right? So long as you're consistent, even if you guess wrong with the direction of a particular arrow, as we'll see as we move through the derivation, um, Newton's second law, will actually sort out for you where those forces should actually be in the other opposite direction instead of the direction that you've drawn them. So provided you've got all of the forces at their correct locations, there's no need, at least in the free body diagram, to worry about the directions because the directions will sort themselves out. So I've got a couple of forces. I've got the force here as a result of the forcing function, which I'll just call capital F as a function of time. And then I've got the spring force acting on the mass, and I've got the damper force acting on the mass. And I am going to play a little trick here. So I'm going to use F prime sub D as the damper force. Also operating in the x hat direction is the friction force. So we'll talk about that in a second. I'm imagining that this mass, even though it's not shown in the schematic, is sliding along some sort of surface, right? Which is what prevents it from just falling in the negative y hat direction. And so we've got gravity pulling the mass down with its weight mg, and then we've got the normal force of whatever surface it's sliding over pushing back up. And then that normal force, because we are sliding over a surface, does induce this friction force. So friction coefficient times n. And the thing that I want to point out here is even though the selection of the directions of the arrows is somewhat arbitrary, it turns out that the damping force from the dashpot and the friction force always act in the same direction, right? So this arrow and this arrow are always going to be acting in the same direction, regardless of whether the mass is moving to the left or to the right. These guys are going to be pointed in a direction that opposes the direction of the force of the mass, right? So they're always pointing in the same direction. Um, that's important because I want to simplify things a little bit to get back to kind of this nice textbook equation. And so I'm going to simplify things by saying, okay, recognizing that the dashpot force and the friction force are always going to be in the same direction, I can just add them together, and this plus sign is always going to be a plus sign because these two guys are always acting in the same direction to oppose the motion of the mass. So I can combine them with a plus sign that's always a plus sign and get myself just to F sub D. So force sub D for dashpot, or maybe D for dissipation if you're a thermo person and like to think of it that way, because that's essentially what these terms do, is they prevent the mass from just oscillating back and forth forever, right? And that's because they provide a dissipation quality that takes the energy that otherwise would just be oscillating between kinetic energy in the motion of the mass and potential energy in the storage capacity of the spring, and they convert that energy into heat, and then dissipate the heat out of the system. And so over time, the dashpot and the friction force will reduce the overall energy in the system and cause the mass eventually to come to rest. If you didn't have that in there, right, think about driving a car. If you didn't have some sort of damper in there to damp out the oscillations and you drove your car over a speed bump, your car would just continue oscillating up and down basically forever. And it would become really uncomfortable and difficult to drive as the car sort of, booping up and down as a result of having driven over the speed bump with no energy dissipation. So the way that the dash pots actually work is that typically they're viscous fluid devices. In 2020 spring, we had the RER artifact was an RC car shock absorber, and the shock absorber, of course, had a shock in it, but then it also had a built-in damper, which was literally just a hole drilled through the piston. And what ended up happening is you move the shock as you compress and decompress the shock, the piston would move up and down, and the fluid, which was kind of a hydraulic oil inside the piston, would just slosh back and forth from one side of the piston to the other through this hole that had been drilled in the piston. And that sloshing of the fluid back and forth and moving it through the hole was the energy dissipation mechanism that prevented that mass spring damper of that RC car shock absorber from just oscillating back and forth forever. So it's sort of the same idea here schematically. Okay, the other thing that I want to do is I'm just going to say that this external driving force is zero at any time greater than zero. And the reason for that, again, is because when we do this thing, solve this problem for the flame tube, I'm going to imagine I'm only worried about, at least for this analysis, what happens after the compression process is over, right? So I've slammed the flame tube down. I've got my auto ignition. My char cloth has got a little ember on it, and now I'm going to let go, right? So release my hand from the piston. And what does the piston do with all of a sudden no force from my hand kind of holding it in that compression? That's ultimately what we're solving for. So at least for that simplification, I could set that force equal to zero, because as soon as I remove my hand, there's no more external driving force on this system. So with those simplifications, I get this guy, which is I've got the force of the damper now, which is I've dropped the prime because I've added again the damper force and the friction force together, and the spring force, both also always operate in the same direction, right? So if I'm expanding or if I'm dragging the mass to the right, um, they're going to operate both to the left. And if I'm pushing the mass to the left, both of these arrows are going to point the way that they are now to the right, because the spring is always going to be opposing and the dashpot's always going to be opposing the direction of movement of the mass with the force that they create. And then, of course, mg up, mg down, and n up. The way that I've drawn it here is kind of as a couple. And I just want to be clear that this is not a couple. It's not inducing rotation. The normal force actually acts through the center of mass like that. But I wanted to draw them in a way that kind of made them more clear that they were opposing each other. And so I've chosen to draw it this way, even though they're not meant to be a couple. Okay, so let me pause there for a second and ask if anyone has questions about kind of how I got to this version of the free body diagram before I get into the equations.
Could you explain again really quick why you got rid of the external driving force? I missed that part.
Yeah. So like from here to here. So if I go, let's see, I've actually got to go all the way to the end. Here we go. Okay, so the process that I am modeling is after all this is done. So I've done the compression. I've got my auto ignition, and now I'm taking my hand off of the piston. So everything is compressed, and I'm taking my hand off the piston, and I'm questioning or wondering what happens to the piston after I remove my hand. And so the moment that I remove my hand, this F of T goes to zero, right? There's no more force that's holding the piston down. And so that just goes away, and the piston will respond by moving upwards, hopefully upwards, in response to the pressurized gas inside the piston.
Okay, that makes sense. Thank you.
Yeah, sure. Other questions while we're here?
Oh, yes. If
Oh,
you can help me, like just visualizing, for example, I like there is like we are modern as a spring and a damper, right? So, in this case of the piston that you just said, um, what would be like the damper or what would be the spring? Like,
aha. I'm glad you asked. We're getting there. Um, and I'll come back and kind of finish. But let me just answer your question. So, in this case, the damper, the energy dissipation mechanism is going to be the O-rings on the piston sliding against the inner wall of the cylinder. Right. So that's a friction process. And so we have to account for that friction, which will dissipate the energy and serve as a damper. And then the spring is there's going to be gas that's trapped behind those O-rings in the piston cylinder apparatus. And that compressed gas, as soon as we remove our hand, it is going to try to push the piston upwards, just like a spring would. It's not a linear spring. We'll see in a second. It's not linear, but it has the same effect of pushing the piston back up to try to get that gas back to atmospheric pressure, given its initial pressurized state.
thank you, got it.
So, yeah, no problem. Okay. Anything else? We're here. Okay. All right. So now we're going to do application of Newton's second law. So it's just F equals ma in the y hat direction. Well, it doesn't move in the y hat direction. So acceleration in the y hat direction is 0. And we're just left with n minus mg equals 0, which is what we expect. So that this mass isn't like falling through space in the y direction. And then in the x direction, the mass is moving. And so it's going to be the sum of the forces on the mass are equal to its mass times its acceleration. And so it's just going to be the spring force plus the damper force is equal to ma. And then if I take that Newton's second law equation and I put in my known expressions for the spring and my known expressions for the damper, I get to the final version of this expression. But let me just quickly explain why I've got these negative signs here. So I mentioned before that both the damper and the spring, those arrows are always going to point in the same direction, right? So they're either going to point to the left or to the right, but FD and FS are always going to point the same way, right? FS always points the same as FD and FD always points the same as FS. And so what this negative sign does is it says, okay, if I'm moving the mass in the positive x hat direction, that's going to make FD and FS in the negative direction, right? Because they're going to try to oppose that motion. And if I'm moving the mass to the left in the negative x hat direction, then FD and FS are going to be as I've shown them here, right? So the arrows are going to point in the positive x hat direction to the right. And so these negative signs are there to give directionality to FD and FS so that when I set up this equation with these forces equal to mass times acceleration, if acceleration is in the positive x hat direction, then these forces are going to tend to pull the mass backwards in the negative x hat direction. So that's what those negative signs do. With those negative signs then in place, I could put my known expressions for linear spring and for Dashpot into my equation, and out pops this guy. And I'm going to just move mass times acceleration to the left-hand side of the equation, leaving everything equal to 0. All the negative signs drop away because every term would have otherwise had a negative sign in front of it. So it's just like dividing everything by -1. And that's it. That's my expression for a standard spring mass damper. And this final version of the equation, all I've done is just drop the x hat notation because the only direction of motion is in the x hat direction. And so it's sort of redundant to leave that there. But this is now a second order differential equation that you can solve for the behavior of this system. And how does it behave? Well, if you initially displace it, right? So imagine we have a true mass spring damper system. If we displace it by trying to compress it, and then we let go, it'll oscillate back and forth in a sinusoidal fashion. But then the damper will also cause that the energy to be sort of dissipated out of the mass spring system, and so the oscillation will fall off as e to the minus zeta omega t, and eventually it'll fall off to zero. And so you guys have, if you've taken vibration or dynamics, you can adjust these different values k, b, and m to get like different damping and different natural frequencies to cause this to be, right now it's under damped, right? But you could cause it to be over damped or critically damped, just depending on what those values are. But in general, the behavior is sort of this oscillation back and forth around x equals zero. And eventually it'll settle to x equals zero after the energy has been dissipated out that you put into it. Okay, so any questions then about sort of the general spring mass damper equation? No. Okay, cool. So now we're going to modify it. And recognizing that we do have, following up on the question from before, we do actually have an energy dissipation mechanism like a damper, which is the O-rings, and we actually have an energy storage mechanism like the spring, which is the gas behind the piston. We can in some way like recycle this equation, right? So there's going to be a spring component, there's going to be a damper component, and then there's going to be a mass times acceleration component. The only difference is the spring force is not going to be Hooke's law. It's not going to be a linear spring, and the damper is not going to be B times X dot. So we're going to need to come up with an equation or an expression for the damping, and we're going to need to come up with an expression for the spring and put those in at this spot and this spot in the standard spring mass damper equation to get the equation of motion for this piston cylinder apparatus after we release it from compression. You guys know me well enough now to know that anytime that I could sneak thermo or fluids into a derivation of any kind, of course I'm going to do that because it's my favorite topics after design. So we've got a gas cylinder spring, and the spring force produced by that spring is not negative kx, right? It's not a linear spring that follows Hooke's law. It's something else. And what that something else is governed by thermodynamics. And as we'll see in a second, until we actually can run some experiments, we don't know precisely what the behavior of this gas cylinder spring is going to be, but we can bound it by two extreme situations, right? And that's what we do in engineering, right? If you don't know how to get the exact answer, you try to figure out what the upper bound is and what the lower bound is, and then you know that no solution can be higher than the upper bound or lower than the upper bound. And in a lot of situations, that's good enough to be able to fully define a system for engineering design purposes. And so we have two cases that are the upper bound and the lower bound. So one bound is an isothermal compression. Isothermal means constant temperature compression. And this is, for our purposes, this is sort of not what you want to do. But let me talk you through it. So now we're talking about the compression process. And I'll just say that when we do the releasing of the piston, it's just an inverted compression, right? So I'm going to solve everything as if I'm compressing, but then all I have to do is set the boundary conditions so that the gas starts out as compressed, and all the equations will still give me the right answer, even if the system is operating in reverse from the way that I'm describing it here. I just think it makes more sense to talk about a compression rather than an expansion when we're talking about a gas cylinder spring. So that's the way that I set it up. So in doing this compression, If we do it isothermally, we're going to be doing it really slowly, right? And so what's going to end up happening is we're going to put in a little bit of work into the piston, and that work is going to go into the gas that's contained in this space. The gas is going to see a very slight increase in internal energy, which is going to correspond to an increase in its temperature. That very slight increase in temperature is then going to be a temperature gradient between the gas and the surrounding wall. And so there's going to be heat transfer from hot gas to cold wall. The wall heats up, and then the wall looks around and sees around it the environment, which is then a little bit colder, and the energy then dissipates through the wall out into the environment. And if we do that process slowly enough, we can do it so that the gas's temperature does not change, and all of the energy that we put into the system by this is now boundary work, PDV work, ends up getting dissipated completely as heat. So the first law for the gas would be just work in equals Q out for an isothermal compression. The other extreme is an adiabatic compression. This is the one that you actually do if you're compressing to try to get the fire tube to produce an ember. So there's two ways to do this. So either you could just do it really fast, right? So you're compressing the gas so fast, it heats up and it doesn't have time to transfer heat to the walls of the chamber or to the ambient environment before it hits that auto ignition temperature and causes the char cloth to spark. Or you could make the cylinder out of something that's insulative, right? Because that's what adiabatic means. Adiabatic means no heat transfer. And so our piston cylinder apparatus is made out of, I think it's aluminum, although I don't know that. We're going to have to check the material when you guys get it in hand. And there's a couple of ways you could do that. A spark test, for example, would allow you to determine the material. I think it's aluminum, but I don't know for sure. But you could make it out of something else, right? So you could make it out of a really insulating plastic or foam or something like that, and then you would have a perfectly well, not perfectly, but pretty close to adiabatic boundary. Or again, you could just do the process really fast. So two different ways to make the process adiabatic, meaning it's not transferring heat from the gas into the cylinder wall or the surroundings. If you've succeeded in making that boundary adiabatic, then what does the first law look like? Well, all of the energy that I put into the system as this boundary work PDV process is all then manifest as an increase in internal energy of the gas. And for an ideal gas, the internal energy is a function of temperature only. And so the gas is going to heat up. So the first law is just going to be Wn is equal to CV T2 minus T1, where T1 is the initial temperature of the gas and T2 is the final temperature of the gas. And hopefully, if we've done the process fast enough to make it adiabatic, T2 is above the auto ignition temperature of that char cloth, and we actually do get a little ember here on the char cloth as we're doing the compression. And just to reiterate again, even though I'm talking about the compression, all of these equations are also true in reverse for the expansion, which is the dynamic model that I was talking about before. I just think it's more interesting to talk about compression rather than expansion. So that's the way that I set this all up. Okay, so how do we tackle these two extremes? Well, an isothermal compression happens at constant temperature. And so you might remember all the way back to even maybe high school or lower division chemistry, there's a thing called Boyles Law, which says that if you have a gas, an ideal gas at constant temperature, that the product of PV for state 1 is equal to that same product of PV for state 2. So P1 V1 is equal to P2 V2. Now P and V can change for sure, but their product is a constant. So as you increase the pressure of the gas, you're decreasing its volume, or as you're increasing the volume of the gas, you're decreasing its pressure, and that product is always a constant. And so we're going to use Boyles Law to try to figure out what sort of force the gas induces on this piston, which ultimately is going to be our spring force that we're going to plug back into this equation to replace this term when we go back into the dynamics analysis. So okay, so how do we do that? So I've got just sort of two definitions here. So one is that the volume of the gas is just the cross-sectional area of the piston, pi d squared over 4, multiplied by the piston displacement. So the entire cylinder has a length L, and the piston displacement is L minus X. Or that's the region that's still gas to be compressed by the piston. So the piston displacement is X, and the region of the gas is L minus X. And so you can see as X gets bigger, L minus X gets smaller, the gas is getting compressed and its volume is going down. And so that cross-sectional area of the piston multiplied by that length of the gas getting compressed is the volume of the gas. The pressure that the gas exerts is just the force divided by an area, right? So the area is the area of the piston, pi d squared over 4, and then the force is here. That's what I'm actually trying to solve for. That quotient is the pressure. So I just set it up this way, and then eventually I'm going to isolate the force by solving for it, and then putting the pressure into the equation. Okay, so with those two definitions and Boyles Law, what do? Well, first I replace the volume expressions with my kind of more detailed volume expression. It turns out that the cross-sectional area drops both on the left and the right-hand side of the equation. Then I'm left with P1 times L over L minus X is equal to P2. Then I come over here and I say, okay, what's P1 and P2? Well, P1 is just atmospheric pressure, right? And why is that? Well, it's because initially I just had air in here, right? And I sealed the air in when I put the piston cylinder, or put the piston in the cylinder. And, okay, maybe there's a little bit of a pressure increase as I'm trying to seat the O-rings. But for the most part, before I actually do the compression, the pressure in there is just atmospheric pressure because I'm not actually compressed the gas. So P1 is just P initial or P atmosphere, and then P2 I get from up here, right? So that's just my pressure expression. And now I want to solve for the force. And so I just rearrange things. And so then I get the force for the gas spring cylinder. The gas cylinder spring for an isothermal compression is just pi d squared times the initial pressure divided by 4 multiplied by L divided by L minus X. So that's that expression. Any trouble with that? Nope. Okay. Then let's move on to the adiabatic compression. So for the adiabatic compression, I'm going to use all the same math. The only thing that changes is the equation of state. So for an adiabatic compression, you might remember from thermo that P1 V1 to the gamma is equal to a constant. And so P1 V1 to the gamma equals P2 V2 to the gamma. What's gamma? It's just a ratio of specific heats. So CP over CV. And for air, that value is about 1.4. And I'm not going to explain or derive where any of this came from because you guys have taken thermo and it'll be in your thermo textbook. But what I will do is use the exact same math that I used before for the isothermal compression to extract an equation for the adiabatic compression, and just replace the pressure with the force like I did before. And what I'm left with is then the spring force associated with the adiabatic compression is just pi d squared multiplied by the initial pressure divided by 4, and now multiplied by L over L minus X, but now raised to the exponent of gamma. So it's a slightly different expression. So let me pause and ask if there's any questions about this one. No, good. Okay. So the reality is somewhere in the middle, right? We can't have a perfect isothermal compression, nor can we have a perfect adiabatic compression. And so what actually happens if you look at the first law is that some of the energy that you put in as a work transfer PDV process contributes to an increase in internal energy of the gas. That's this term. And then some of it contributes to heat transfer out of the control volume of the gas into the wall of the cylinder and then out into the environment. And it turns out that is called that combined increase in both internal energy and heat transfer simultaneously is called a polytropic process, which you might remember from thermo. And the good news is that the equation that governs a polytropic process is basically the same as the one that governs the adiabatic process, except instead of using gamma, I use N, and N is some value between 1, which is an isothermal compression, and gamma, which is an adiabatic compression. And so I get the exact same equation, except instead of gamma, I've got N here in the exponent, but otherwise it's completely the same. And the reality then is, if I go to my annotation tool, the true spring force. So I've got here displacement on the x-axis and a force on the y-axis. The blue dotted line is the adiabatic compression, and the red solid line is the isothermal compression. And as you would expect, the adiabatic compression is much higher, right? Because we're not letting any of that any of the energy that we put in out as a heat transfer process. But what actually happens is this polytropic compression, which I'll try to draw here, which is somewhere between those two, right? And I'm not drawing it very well, but that's sort of what that polytropic curve looks like. And how high or how low that polytropic curve is depends on the value of N. And the only way that you could really know that is by running an experiment, right? So you'd actually instrument a piston cylinder apparatus, do the compression, figure out what the temperature increase of the gas is, plug that temperature increase in here, solve for Q, and then determine the polytropic exponent based on the ratio between the change in internal energy and the heat transfer. So that's how that would be done experimentally. Okay. Any questions about the thermo? No. Okay. Well, so the good news is we've got our spring expression, and now with about a minute to go, this is how you do the damper part of it. So we've got an O-ring. The O-ring is sliding up and down the surface of the cylinder, and it's dissipating energy in the process. Although that energy dissipation is not the fluidic sort of dashpot B X dot that we got before from a conventional dashpot. It's actually a constant, more or less. It's a constant that has a pressure function in it. And so this is why at the beginning of class I dropped the Parker O-ring handbook into the chat, because all of this just comes out of the Parker O-ring handbook, and I'll post it on Canvas so that you guys can see it. But for a piston groove, which is what we've got, the equation is darn it. Okay. It looks like I erased the equation by accident. Okay, the force equation is just the sum of FC and FH. So I'll change that when I post the final slide. So the total friction force, F sub D, is just FC plus FH. What's F sub C? Well, that's the friction due to O-ring compression. And then what's FH? It's the friction due to fluid pressure. How do I get those values? Well, F sub C comes from this chart in the Parker O-ring handbook. So I get a percentage of seal compression, which is, I just take my O-ring, I measure it uncompressed, and then I determine how much compression it experiences when I put it into the piston cylinder apparatus. That's my percent seal compression, and then I just pluck the friction force per unit length off of one of these curves. These curves are based on the hardness of the material, which is another material property that you just look up in the Parker handbook. It's this chart after determining what the material is. So for example, a hardness of 70 corresponds to silicon, right? So here's silicon, and there's a value of about maybe about 74 there for silicon. F sub H, how do I get F sub H? Well, I pull that off of this chart. So I need to know the fluid pressure, which again, I can get from thermodynamics, and just use the fluid pressure to determine lowercase F sub H. And that's what gets plugged in here. And then I need an LP and an AP. Where do I get those? Well, those come out of a table in the Parker Handbook. So it's a table in chapter 5, which I don't have time to show because we're at the end of class. But that's where those values come from. So you measure the O-ring, and then you pull the value for LP and AP for a piston groove out of that table. We do have a piston seal as opposed to a rod seal, so I just wanted to mention that. And now we're at the final step, right? Which is I've got my original spring equation here, and all I have to do now is plug in my expression for Fs and my expression for Fd into that equation, and I get my new dynamic equation. So here's the gas spring part, and then here is the part, the dissipative part associated with the O-rings. All of these terms come from values that I look up. And then this is just still the mass times acceleration. So once I've got this thing compressed and I let it go, this equation governs what will happen, what the piston will do. Okay, so let me stop there because I'm a little bit over time, but I'm happy to stick around and answer any questions if people have them that are relevant to the lecture. So questions if you've got them. No. Okay, great. Then let me stop sharing and stop recording.